Welcome to Math with Malia. Today we're doing Savvas enVision Algebra 1, Topic 4, Lesson 3, Solving Systems of Equations Using Elimination. After this lesson, you'll be able to solve systems of linear equations using the elimination method. So the previous lesson we did substitution. Today we're going to see when it might be better to use the elimination method. For the critique and explain, we have two students, Sadie and Micah, solving this system of equations. And you can see Sadie's work on the left. She used substitution, so she saw that y equals everything in parentheses, and so she substituted that into the second equation, solved for x, and then plugged that back into the first equation to solve for y. Micah, on the other hand, what he did was, it looks like he rearranged the second equation. He moved the 4x to the other side. Actually, he probably just moved the 5 over and then moved the negative y to the other side. So he rearranged and turned the second equation into slope-intercept form. So then it was 4x minus 5. And then since they're both equal to y, he set them equal to each other, solved for x, and then plugged it into the first equation to solve for y. Both methods got the same solution, but they went about it in slightly different ways. So which one would you think would be the best way? They both work, but I would say Sadie's method would be most efficient because you didn't have to manipulate the second equation. You already have substitution set up for you to do. So that's something to keep in mind. You're going to have a choice of which method to do. You want to choose the most efficient method. So when will we use elimination when we're solving a system of equations? Well, typically, if you see a system of equations where both equations are in standard form, you do not have one of the equations in slope-intercept form or saying x equals something, then you can probably use elimination so that we don't have to rearrange one of the equations to get it into slope-intercept form. So here, for example, 1, you can see two equations are in standard form. We have both variables on the left and the constant on the right. So to do elimination, it's called elimination because we're going to eliminate one of the variables. We need to get rid of one of the variables. We can't solve two variables at the same time. So if we add the two equations together, you can see we have the two equations here. If we add them together, we can eliminate the y variable, positive y minus negative y. That will cancel out. So we've eliminated the y variable, and now we have 3x's on the left equal to 9 on the right. We can solve for x and get x equals 3. This works because of the additive property of equality. Essentially, what it's saying is 2x minus y is the same as 2. It's equivalent. So we're really just adding a value of 2 to each side because 2x minus y is the same as 2. So I can add the same thing to both sides of an equation, and because of the property of equality, I will have an equivalent equation. I'm not changing anything. And then when you regroup, then you combine your like terms, and you can see we can eliminate the y variable. So this is because of the addition property of equality. After we solve for x, then we plug that value into one of the equations, choose the simplest equation, so choose the first equation, plug in your value for x and solve for y, and you get your solution, your ordered pair for the point of intersection of the two equations. Try it number 1. Let's solve this system of equations using elimination. So again, you can see we have both equations in standard form, so we're going to add them together. I'm going to rewrite them down here. So which variable are we going to eliminate? Are we going to eliminate the x variable or the y variable? Well, we can see just by looking at it, I can cancel out the y variables already. You want them to have the same coefficient and opposite signs. So you want the variable to have the same coefficient and opposite signs. That means if you add them together, they will cancel out. So 2x's minus 1x is 1x. That's 0 equals 5. So we already have our x value. Plug that into one of the equations. Let's do the first one. So 10 minus 4y equals 2. Subtract 10, 4y equals -8. divide both sides by -4, y equals +2. So our solution for the first one is 5, 2. Okay, let's do letter B. I'm going to rewrite them over here. 2x plus 3y equals 1. -2x plus 2y equals -6. So already I can see that the variable I'm going to eliminate is the x variable. They have the same coefficient and opposite sign, so I know when I add them together, they will cancel out. 3y's plus 2y's is 5y equals -5. Y is going to equal -1. So now I've solved for the y variable. I'm going to plug that into one of my equations. So 2x plus 3 times -1 equals 1. 2x minus 3 equals 1. Add 3 to both sides. 2x equals 4. Divide both sides by 2. X equals 2. So we have our ordered pair for the second system. Our solution would be 2, -1. That would be the point of intersection. So again, using elimination, you're trying to cancel out or eliminate one of the variables by adding the two equations together. Example 2. How can we verify that this elimination method actually works? We'll take our solution, 1, 2, and see if it works. Okay, so they're telling us the solution is 1, 2. Let's plug it into both equations and see if we get a true statement. So plugging in x for 1 and 2 for y, I get a true statement, 7 equals 7. And then plug it into the second equation, so 2 times 1 plus 2 times 2. 2 plus 4 is 6. That is a true statement. So that solution does make both equations true at the same time. You could also graph it, so graphing those two equations, and verify that the point of intersection is at 1, 2. So what happens when we have a system of equations, but we don't have a variable that has the same coefficient and opposite signs? So here's our system. Looking at the x's, I have 1x and 2x, so they don't have the same coefficient, and the y variables do not have the same coefficient. Well, thinking of our property of equality, if we apply the operation to both sides of the equation, we can create an equivalent equation. So if we multiply the top equation by 2, I will then turn the x coefficient into a 2 with the opposite sign. So now my x variables have the same coefficient with opposite signs. So all we did is we multiplied the whole first equation. So make sure you're multiplying the whole equation by -2. I like to put parentheses around it to remind myself I need to distribute the -2 to every term inside the parentheses, including the constant. So -2 times x gives me -2x. -2 times 3y gives me -3y. Don't forget to multiply by the constant. And now I have a new system, and I can add those two together and solve for y. So y now equals +2. And then I can plug that into one of my first equations. Let's plug it into the first one because we're solving for x. X plus 3 times 2 equals 7. X plus 6 equals 7. Subtract 6 from both sides. X equals 1, so my solution should be 1, 2. All right, let's try number 2. We have a system of equations. We're going to have to create an equivalent equation for one of the equations so that we can eliminate one of the variables. If I'm looking at part A, I'm going to eliminate the x variables because I know I can easily turn 1 into -2. So how do I turn my coefficient of 1 into -2, because it needs to be the opposite sign of the other coefficient? Well, I'm going to multiply everything by -2. So then I like to draw arrows, and I'm going to rewrite both equations. So after I distribute the -2, my new equation for the first one becomes -2x minus 4y equals -8. Don't forget to multiply by the constant. Then rewrite the second equation in the system and add them together. So my x variables cancel. I have -9y equals -9. Y is going to equal 1. Plug that into one of the equations. Let's plug it into the first one, x plus 2. So make sure you're plugging in your variable into the right place. Always write your variables. Keep track of which variable you're solving for. 2 times 1 equals 4, so x plus 2 equals 4, x equals 2. So my solution for the first one would be 2, 1. All right, the second one, same thing. So we can choose, we can do either the x variable or the y variable. Let's eliminate the y variable this time. So I need to multiply the first equation by positive 2. Okay, so I'm going to rewrite the equations after I distribute. 2 times 2x is 4x, 2 times y is 2y, equals 2 times 2 is 4. Don't forget to multiply by the constant. Rewrite the second equation, lining up your like terms, so that's important. Make sure you line up the x's and line up the y's. Add the two equations together. My y variables cancel. I have 5x equals -1. X equals -1/5. Plug that into one of the equations. So -1/5 minus 2y equals -5. So I'm plugging it into the second equation. Add 1/5 to both sides. -2y equals -24/5. Divide both sides by -2, which is the same as multiplying by -1/2. Positive 24/10. Simplify that, it gets to be 12/5. So my solution for the second system is -1/5, positive 12/5. So again, leaving it as fractions so we get the most accurate answer. These ones are not going to be irrational decimals, but get used to writing them as fractions. Example 3, our application problem. A customer chose decorative garland and a rangoli flower design that they want to decorate their home for Diwali. The florist has 853 marigolds. That should actually be 852, so change that, that's a typo. 852 marigolds and 732 mango leaves. So we have a limit. These are constraints. We have a total amount of the flowers. We can't do more than that. How many of each decoration can we make? So if you look at the question and the word problem, that can help you define your variables. My variables need to tell me the number of each design. So the number of garlands and the number of rangoli flower designs. So you can see here, we've said X is going to be the number of garlands and Y will represent the number of flower designs. And in the graphic, you can see how many of each type of flower it takes to make each design. It takes 38 marigolds and 58 mango leaves to make the garland. It takes 132 marigolds and 12 mango leaves to make the flower design. So we're going to write an equation for each type of flower. Okay, so our total marigolds is 852. That's our limit. We use 38 marigolds for the garland. So this is our garland. And then we use 132 marigolds for the rangoli flower design. Okay, for the mango leaf, same thing. We have our total, 732. That's our limit. We use 58 mango leaves in the garland, and we use 12 mango leaves in the flower design. So that's how we come up with our equations for our system. Each equation is specific to the type of flower. And then we're solving for X and Y. Okay, so we're just going to use elimination. We need to eliminate one of the variables. Can we multiply one of the coefficients to make it have the same coefficient, the same number, but opposite sign? Well, lucky for us, we can eliminate the Y variables, okay? We can multiply 12 by -11 and get -132. So we're going to do that. We're going to multiply the whole second equation by -11. And let's rewrite those. So I didn't change the first equation. I'm just going to rewrite it. And distributing the negative 11 to everything, I get negative 638 x's, negative 132 y's, that's what I'm going to eliminate, equals negative 8,052. So 732 times negative 11 is negative 8,052. I'm going to add those together. We can see we'll eliminate the y variable. I get negative 600x equals negative 7,200. Divide both sides by negative 600, x equals 12. Okay, so I found part of my answer. The number of decorative garlands I can make is 12, so 12 garlands. How can I find the number of flower designs? Well, plug that into one of the equations. Let's plug that into the first equation. So 38 times 12 plus 132y equals 852. We get 456 plus 132y equals 852. Subtract 456 from both sides. 132y equals 396. Divide both sides by 132. Y equals 3. So we can make 3 flower designs. Okay. So our solution, I'll write it up here, if we were to write it as an ordered pair, would be 12, 3. Make sure you keep track of your variables. Don't mix them up. For try it number 3, before the florist has a chance to finish his order, a large order is placed. After the order, only 360 marigolds and 360 mango leaves remain. So now we have different constraints, different limits. How many rainbow flower designs and decorative garlands can the florist make now? So same thing, X is going to represent the garland. Y is going to represent the flower design, right? The number of each. So let's write those equations. I have, the graphic is still the same, so I still use 38 marigolds for the garland, and I still use 132 marigolds for the flower design. And now my total, my limit is 360. Okay. For the mango leaves, I use 58 mango leaves in the garland and only 12 mango leaves in the flower design, and my total is still 360. And we need to eliminate one of them. So we're still going to multiply one of these, the second one, we're still going to multiply by negative 11 because the coefficients are the same. So the only thing that's different is the totals. Okay, so we have 38x plus 132y equals 360. And then we're going to get negative 638 again, x, and negative 132y. But my total now is going to be negative 3,960. So the only thing that's different is our totals. Add them together. We're going to cancel out the y variables. We get negative 600 equals negative 3,600. Divide both sides by negative 600. X is going to equal 6. So we can make 6 garlands now. 6 garlands. That makes sense. We have less flowers to use, so we should be able to make less of the decorations. Plug in that value into the first equation. 38 times 6 plus 132y equals 360. We get 228 plus 132y equals 360. Subtract 228 from both sides. 132y equals 132. Y equals 1, so we can make 1 flower design now. So our solution, if we wrote it as an ordered pair, would be 6, 1. That makes sense because we have less flowers to start with. Example 4, what is the solution of the system of equations? So now we get to choose the method. Take a look at your system. Which method would be most efficient? Well, I can see my first equation is already in slope-intercept form. I already know what y equals. I'm going to use substitution. That would be the most efficient. So just substitute whatever's in the parentheses in for y in the second equation and distribute and solve. We get x equals negative 9. Plug that into the first equation and solve for y. So again, I use substitution because I already had what y equals. I could already substitute that in. I didn't have to manipulate any equations. For the second example, I have both equations in the system in standard form, so instead of rearranging and turning them into slope-intercept form, instead of moving the x term over and then dividing by the coefficient, that would take extra work. Let's just multiply by a constant and get an equivalent equation. So I'm going to eliminate the y's. That means I need to turn this into positive 4. Let's multiply by negative 2. It'll turn it into positive 4. That will cancel out the negative 4y. So after we do that, we get negative 16x plus 4y equals, don't forget to multiply by the constant, equals 16. And then rewrite the second. Okay, and then you can see here, we add them together. We get 11x. Negative 11x equals 33, so x equals negative 3 as we added the equations together. Plug that into one of the equations. They plugged it into the second equation. Substitute x into one of the equations, it doesn't matter. You'd get the same answer if you plugged it into the first equation. And then we get our solution. X is negative 3, y is negative 8. So just make sure you watch the signs. Okay, I needed to turn this coefficient into positive 4, so I needed to multiply by a negative 2. So make sure you're checking the signs so that it's the opposite sign as the other coefficient. Try it number 4. Let's choose our method. For part A, they're both in standard form, so I'm going to use elimination. Okay, I can see, well, we can choose to do either one. We could either eliminate the x's or the y's. It doesn't matter. I'm going to multiply by 2. That might be easier. So I need to turn 3x into negative 6. How do I do that? I need to multiply it by negative 2. Okay, remember it has to have the same coefficient but opposite sign. Then rewrite the two equations after you distribute. This becomes negative 6x. This becomes positive 4y. Negative 2 times negative 27 is 54. Add the two equations together. I cancel out the 6x's. I get 16y equals 48. Divide both sides by 16. Y equals 3. So I'm halfway there. I know my y coordinate. How do I find the x coordinate? Plug that into one of the equations. I'm going to do the second one. 3x minus 2 times 3 equals negative 27. 3x minus 6 equals negative 27. Add 6 to both sides. 3x equals negative 21. X is going to equal negative 7. Okay, let's do the second one. Part B, I can already see what x equals. So I'm going to use substitution. I'm just going to substitute whatever's in the parentheses into the first equation. So 3 times everything in the parentheses minus 2y equals 38. Don't forget to copy the rest of the equation, then distribute. 18 minus 3y minus 2y equals 38. Combine my like terms. 18 minus 5y equals 38. Subtract 18 from both sides. Negative 5y equals 20. Divide both sides by negative 5. Y equals negative 4. So I'm halfway there. I'll write this one here. My solution is negative 4. How do I find x? Well, let's plug it into the second equation. That will tell me what x is right away. So plug that in. X equals 6 minus, what am I subtracting? Whatever y equals. So make sure you plug in that value. It's helpful if you add extra parentheses so that you know you're not missing any negatives. I'm subtracting negative 4. So x is going to equal 10. We made it to the concept summary. Choosing whether to use substitution or elimination, just make sure you check how your system is set up. If you have an equation that tells you what one of the variables equals, you can use substitution very easily. If both equations are in standard form, then you need to multiply. One or sometimes both. If you look in this example, you have to multiply both equations to eliminate one of the variables. So we had to multiply we're eliminating the x variable, so we had to multiply the first equation by 5 to get positive 15x, and then we had to multiply the second equation by negative 3 to get negative 15x. So sometimes you do have to multiply both equations by a constant so you can eliminate one of the variables. And then make sure you keep track of which variable you're solving for. Okay, write those down carefully. And then you plug in that value to find the other variable. If you have any questions, put them in the comments. Make sure to come back for lesson 4.